So I'm happy for it to be on Broadway. So I work for Google. I'm from the Waterloo, Canada office, and I lead a team of 5 engineers who work on foam full-time. The presentation is itself a single-page JavaScript foam app. So this is really a case of the medium being the message. Everything that you see today is a foam. All the screenshots, except for one, are screenshots of other foam programs. So, including this animated foam logo. This is actually something I've been working on for 26 years. So, only 3.5 years at Google. So this is really the culmination of my life's work to date. So I hope you like it or I'll feel rejected. Okay. So how many people, at raise of hands, have ever heard of model-driven architecture? Okay, so not very many. Oh, and by the way, these slides, you can go to foamdev.com, and they're there, and they're interactive, so you can play with them and have a lot of fun. So I'm not very good at anything other than programming, so I didn't want to draw a lot of images, so I thought I have 25 minutes, I'll just write 25 demo programs, which is, if you ever get that idea, not a good one. Okay, so as I said, foam stands for feature-oriented active modeler. And so what it is, in JavaScript you have lots of MVC frameworks, but foam is something a bit different. It's a modeling framework. And what this is, a model is like a high-level representation or specification or abstraction of some kind of anything, really. Like a blueprint. So like a UML diagram is a model. But normally that UML diagram like dies on the whiteboard. You kind of chart it all up, and then you go and convert that to software by hand. And what foam does is let you create these models, and then it converts it to software for you. So this is a big time saver. So here I have a little grid, and on the vertical axis I have a bunch of models. And you'll see a lot of these in the presentation today. So that's what a model is. And then a feature is anything that we're building or generating from those models. So it's like a reusable concern. So if I look at a model, then I can generate the help view for it, a detail view, a table view, a summary view, XML adapter, JSON adapter. And this one is interesting. This is actually the Java code. So this is not just a JavaScript framework. When you create this model, then I could go to, it's not done yet, but I could go to an Android conference maybe next year and give the same talk with everything, the models being adapted or converted to JavaScript. Or a UML diagram, or sort of thing like JS docs. Now if you notice, even the first column is model. So actually our model is itself modeled, which is kind of presents some bootstrapping issues, but that's what makes the system very small and very powerful. And so it's not, superficially at some points it kind of looks like a view library, but it's not. Views are just sort of 2 or 3 columns in this feature grid, but we actually have like 30 or 40 features implemented so far. So once you create the model, all of those features you kind of pick up for free. Okay, and so we can just go over here, and you can see all of them. So there's about, and just in this grid, there's, I think, 25 models and however many. So if you were to go to code all of these components by hand, that would take you quite a while. But here what you're just coding is your models and the reusable generic features. Okay, so now we're going to step back for a second, and we're going to have a little bit of a history lesson. So what I'm running now, this is a simulation, and the dots represent programmers. And the green represents code. So we have these developers running around writing code for the various data types on the left. So this is an operating system, Multics, and all the data types, they're things that you would need for an operating system: users, groups, processes, devices, files. And then all the features that you would need: sorting, search, paging, printing, editing. So this is, if you wanted to make an operating system, this is how you would do it. So Multics, historically, this was a big project being written by General Electric, AT&T, and MIT. It was because writing an operating system at that time was such a huge project. And on the right, we had Dennis Ritchie and Ken Thompson, two guys who wrote Unix. And what they did was they didn't run around filling in the cells. They created reusable components like sort, grep, more. And then they used the pipe command to chain those together. And then all of the individual commands, they just left out all those features. So Unix was feature-oriented. Okay? So on Multics, if you do 1 unit of work, you get 1 unit of utility. In Unix, it's actually, if you do 1 unit of work, you're going to get n units. So you can see I've charted here, it's running, it's charting the utility, and at this point, right there, Unix has actually overtaken it, despite having 50 times fewer developers. And so this is really the point of Foam, is that we're trying to increase your productivity exponentially by really making it that you only need to code up the perimeter, not the area. Okay? But something else interesting they did with Unix, it was written in a high-level language for the time, C, which was pretty controversial. And then when new platforms came in, they could easily port that to the new hardware. Whereas the Honeywell hardware that the Multics was written in, when that faded into obscurity, Multics went with it. And we're still running Unix or variants today on iOS, Android, Chrome OS, Linux, and whatnot. And you can see now once this happened, the utility has spiked even more, because now you didn't need to rewrite it for every new hardware platform. Okay. So Foam is what we like to refer to as a holistic system. So it's end-to-end. We create this model, and we can generate a whole system from it. So if you look at the way kind of applications might be written today, and you can change this diagram to whatever your technology stack is, and each language is in a different color. So the backend SQL is green, then say this system is with a backend server in Java, then say protobuf or Corba or RMI or some other kind of middleware, and then JavaScript on the front end, and then HTML on the front end of the front end, and then CSS. So we're 1, 2, 3, 4, 5, 6 different languages. Now, one thing you probably hear a lot about is dryness, which is an acronym for don't repeat yourself. And that's why we have a constant. So we might, in some system, we might say that the width of a last name is 35 characters. And that way, if I want to change that, I only have to change it in one spot, so it's less work for me. And then it also makes the system more reliable, because I don't change it in one spot and not another. But there's no way to do that in modern systems that span multiple languages. It doesn't help me to make a Java constant for that size when I still have 6 other languages. So if you use something to generate your middleware, that's also a type of model. It's just very limited. So if we get rid of that and drop in a Foam model instead, then the code that we generate, we can push out. And now that the last name's width is 35 characters, is only defined in one spot. But in fact, that the person even has a last name is also now in only one spot. And then we can also add, we have support for client-side caching and rich client-side search. And then what we hope to do in the future is actually add more platforms. So now on the server side, we can do Node.js and some Java, but in the future, we hope to do Android or other client-side apps as well. And so you never have to rewrite code that you never wrote in the first place when you want to add more platforms. Okay, so here's a little game of Pong. And Foam, what we do is we model like classes in JavaScript, and we add a lot of sort of the missing features from JavaScript. Like packages, inheritance, traits, inline templates, reactive programming, type checking, runtime type checking, properties, interfaces, constants. So this is the whole kind of class of semantic sugar. And we do this all without a transpiler. And what that means is when you get if you're in your debugger or in your profiler, you're actually going to see the code that you wrote in the file you wrote it in on the line you wrote it. It's not going to be kind of messed up and that isn't complicated. But if you want to use a transpiler, then we're not preventing you because we're not transpiling already, so we're compatible with that. But we can add all these features with that one. And so several of these features, you can go through this demo and you can open up and get more an example. But here's how we define a class. Here's the package and requires. You can say what you extend, and then just call this.super. We have traits, which give us multiple inheritance, constants, properties, which are like variables, but you can associate factories or pre or post conditions or lots of other things with them. Listeners, actions, inline templates. And so it makes it a very pleasant language to program in. And people who use Foam a lot often comment it as though it's a different language, although it's not. It's actually just straight JavaScript. We also have dependency injection, so here's a little 200-line Minesweeper game. Oh, I died. And here's how we do the dependency. So you can click on these, you can see the source. So we have requires, which are the models that you require. And then we also have exports, so you can export the features that you want to inject into your descendants, and then you can do your imports. And so here this one is empty, so I'm actually exporting myself, and I'm naming myself board. And then so the board is exporting itself, and then cells can use it. So all the objects in Foam are kind of self-centered. You list your requirements and your imports and your exports, and then they all become properties on you that you just access as this dot. But then if you want to mock them out or do testing, you can just always set them as normal properties. So every object in Foam, they're very modularized. We don't use globals, and everyone just knows about itself. Okay, so we can actually model anything. We model classes or entities, and that's sort of the default. And when we talk about that, we'll just usually call those models. But we also model animations, which you've seen already. We model our database queries in a high-level abstraction, so depending on what database we go to, we can target that specific database. We model parsers, so you might use like regex expressions, but we have context-free grammars, which are more powerful. We have an app, it's in the Chrome App Store you can use, called the Chrome App Builder. And what we do is we model kiosk and digital signage apps, which is a big use case for Chrome OS devices. And you can just use that app, fill in a bunch of forms, and it'll make you an application. So that is a Foam app, and it generates Foam apps, but you don't even have to be a programmer to use it. And so with Foam, we're really trying to do two things. We're trying to extend the range of programming. We're trying to make it easier on the low end for people who are maybe junior programmers or not programmers at all. And then we're trying to extend it on the high end so that kind of extend the reach of even very experienced developers. And so this app actually has 13,000 users in the last week, so it's quite popular for people who are not even mostly programmers. So here's the architecture, and again, this is sort of one of those Foam animations that we modeled. Notice the cool reflections. Okay, so we build on top of JavaScript, a very powerful event model. On top of that, reactivity, then animation. Then we have an MVC layer, metaprogramming layer. And from this, and then we have what we call the integrated modeling environment, which is like an IDE. But we can also generate Java, Dart, C++, and code for other languages as well. Now here comes the developer back from the original. And one thing that we're careful about is that we make every level accessible. So sometimes with very high-level frameworks, that's great for the things they let you do, but for other things, they kind of get in your way. So we make sure if we don't make something easier, then at least we don't make it harder. And you can always break down to any level, including JavaScript. Okay, so probably most of you are familiar with To-Do MVC, which is a sample app written in many different frameworks. Foam is listed there now. You can have a look at the source. It's quite short. It's much shorter than many of the others. So point here is Foam is not an MVC framework, but we needed some kind of views to bootstrap the system, but you're free to, target any other, your favorite view library. Okay, on the DAO, on the model layer, actually that's an issue. So Foam is feature-oriented active modeler, and what we're talking about is a model which is sort of like your schema or your blueprint. But in MVC, you have model as well, which is a different model, so the word is overloaded. And the problem is Foam, usually you're one system or another, but Foam does both. So in Foam, if I say I have a model that has 4 different meanings, and they all make sense in Foam. So normally when we say model, we mean the modeling model, not the MVC model. And usually it's clear from context. So if we want to store a whole collection of objects, we use the DAO interface, which is a data access object. And so here's the interface, has like common things you would expect: put, remove, find, select, remove all, update, listen, etc. And here's how you would use it on the right. So I take the DAO, I can say skip, limit, order by, where, and then I can do and, EQ, or greater than. These things like email.timestamp, these are generated from the model. And then I can do a select into group by, the subject, and the count. So this looks very straightforward. And it's kind of easy to use. And if you click on this example, I don't think I have time, there's lots of nice examples. And we even have some that are graphical. So I can say, instead of group by, I can say pie, and that will give me back a graphical pie chart. Or I can say grid by, which is like a 2-dimensional group by, and I can say grid by pie, and I'll get a 2-dimensional grid of pie charts just in one line. But how does that work? So here's our to-do MVC app, and most of the to-do MVC apps all go to local storage as part of the specification. But that's not very scalable. If we wanted to switch to IndexedDB, because that code is not coded directly to local storage, it's actually coded to the DAO interface, and we have different implementations. So anything that's in kind of pinkish red is actually a strategy. So it's something that really stores data. And in one line of, if I can change one line of code, then I can switch to IndexedDB. And I can switch to all these other ones, or I can go with a REST client and go across to a server stored in MongoDB, or we have a bunch of decorators that we can use to add different things like timing, caching. We have several caching strategies, like time to live or LRU or whatever. So we really support nicely offline apps by using the various types of caching or synchronizing decorators. This is a graph of our performance performed by another team for their app. It's on average, it was 99.7 times faster than IndexedDB, even though it is storing it in IndexedDB itself just by adding caching and query optimizing. Okay, so we have view library, we standard kind of DOM views, but one thing we also add are canvas views. Now there's a lot of things though that you kind of get for free from the DOM, like data binding, and so we add these things to our graphical views. So here I can move the gauge around. Now when I give you a view, you don't know if it's DOM or Canvas or maybe even WebGL. It's the same interface and it's transparent to you whether it's graphical or text or a combination. Event handling, so this is a Canvas button. Configuration, I can configure that. Composition, so I can combine 2 circles to create an eye. I can combine 2 eyes to create eyes. I can combine those into this creature. We add reactive programming so it can make the graphics react to other things in the environment. We add animation and interpolation. So even though I'm going to animate something, I can say what's the interpolation curve I'm going to use for that. Now you get this with CSS, but only for DOM, not for graphics. And now this works for anything regardless of how it's implemented. Even things that are not visual, like I could animate your salary, for example. So here we'll look at some code. So here I'm going to say I've created a clock and a mouse. And I just say the clock's X is the mouse's X, and the clock's Y is the mouse's Y. But notice that each of these variables have dollars after them, and that means I want to make that a live binding. So now if I move the mouse around, that's live. So we have like this kind of two-way data binding, but not just for DOM values. It works also for Canvas, or it works for any value on any object, whether it's graphical or not. Or I can do something like this. And so this is really like how spreadsheets work. You don't have to add listeners and callbacks. You just say that it's a formula, a function of something else, and the system does that for you. So now I've said that the second clock's x is the first clock's x plus 200, and that, you know, causes a network of that. Okay. Comment these out. And replace them with these versions. And now these ones, I'm doing some stuff, but I've modeled time, and I have a timer. And when I run that, now we get animation. So actually, the interesting thing here is we didn't do anything special. We just treat time like a normal object, we react to it, and then we get an animation system for free. And then we can put it all together, and we can have all kinds of fancy reactive animations. These are all reacting to time. I have this time wheel, but it's not a function of time, it's a relation of time. So it's not a slave, it's a peer. So if I grab it, I can stop time, I can go backwards, and I can kind of spin it like a DJ. So there's nothing special about time. I have a, you know, explicit control of it. It's just another value. Same thing. If those formulas that we use to react happen to be formulas from physics, then we get physics. And so we don't have a physics engine, but I can do collisions, or collisions with springs. Okay, this one's like a lava lamp. It takes a while to get interesting, so I'll skip it. Or, there. Okay, so we did reactivity. We got animation for free. We got physics almost for free. But if you recall earlier on, I said that we modeled our models. So just as this dragon is a function of time, he's also a function of his own code. So if I look at, here's the wing code, the feather code, and the main one. If I go in here and I find where we draw the tail, and I'm going to comment that out. So you notice actually I got the syntax error right on the keystroke. And I press no, it's fine. So now it's more like a kind of a bat. Let's go up, change the wing. So we'll change the amount that we rotate. Let's go a bit more. Now how much let's make the feathers longer. Okay, that's pretty cool. Now it's going a little fast though. Let's slow that down. So we have a time warp on our time. We've modeled time. So I'm just going to, let's make that 20 times slower. Okay, that's pretty cool. And so as I mentioned earlier that we don't have any transpiler. We just press F5 and we have the new code. We don't even have to do that. We can just modify the code while it's running. Wow, that's pretty cool. Stop it. Okay. And again, we didn't explicitly try to make a live coding system. We just have this reactive, and we have our modeled models, and it just happens. So a lot of MVC layers are really mostly view layers. We have the DAO for the data, but we also have reusable controllers. And that's basically like the whole app. You just plug in a DAO to get the data source, a model so it knows what kind of data it's working with, and then your app is done, and a few custom views. So if you look at something like Gmail and Outlook, they're basically, Outlook and say iTunes, they're almost the exact same app. They've got the same structure, and it's just different data that you plug in. And so you can click on these, and you can try our version of Gmail, and and it works quite nicely. But the thing that's interesting is it's only 900 lines of code, and that's incredibly small. And it works perfectly well offline. It'll sync the data when you come back online. It lets you do offline search. It also lets you sort, and it'll do search on the keystroke. Okay. Toolability, I'm running a bit behind time. So just like in Lisp, where your data structure are lists, so it's very good for doing this kind of metaprogramming, our data is models, so we can do lots of kind of metaprogramming or toolability against them. We create these UML diagrams, and there's nothing special about that. We can just go to the DAO. All of our models are in the DAO, and produce those kind of queries against it, and away we go. We have a tutorial. You can go to that and learn how to do some foam stuff. Here's the calculator app. If you've ever used Chrome OS, the system calculator that comes with it is written in foam. It's all animated. And you can give that a try, and it's really neat when you resize the window, it animates it. This app, I'll skip this, so this is basically a system for doing wikis. This presentation itself is written in foam. So in summary, so this is sort of like, why do we care? This is an animation similar to the original one. It started off with two developers, let's call them Larry and Sergey, and had web pages and search being the first model and the first feature. But now this is growing, and so just like the Unix model, this is sort of a three-dimensional problem. And if you want to solve this, by having to fill in that whole area, that's a lot of work. But if instead we can move those developers to the perimeter, that becomes then exponentially less work. So foam is model-oriented. Models are modeled. Gives you language-like features without a transpiler or without having to upgrade to the next version. Better toolability, cross-language dryness. It's feature-oriented. A big part of that is our reactive MVC, though we're free to plug in any other view library or data source. It's reactive. That gives us animation, physics, and live coding very easily. Our models are DAOs. They're technology independent. We can go to different data sources. And we have all these decorators that we can do to add extra functionality a la carte. We have great offline support. We have views. The thing that's interesting is that we can go, whether it's graphical or DOM, and you can't tell the difference. And we're cross-platform and cross-tier in that we can support Java and Node.js. So basically, this is an operating system for information, not in terms of like device drivers and a file system, but literally like a system for operating with your information. We don't care how you want to display it, where you want to store it, or even what language you want to use for that. We abstract that away. And so really, the summary of the summary is efficiency is really foam's value proposition. We're talking about application performance and developer efficiency, or as we like to just say, is foam is for fast apps fast. Thank you.